but we're going to spend some more time looking at Matlab and trying to understand some of the relationships that we looked at last week with the Fourier transform. I can find my markers. I can't. So, just a reminder, I'm going to start by giving you a few Matlab tricks, but just as a reminder, this is what we're looking to emphasize today. We talked about this signal, minus A, 1 over 2A, and we decided that when we take its Fourier transform, we get sine of A omega over A omega. And if we were to plot sine of A omega over A omega, we get the sinc function. And what I keep plotting when it looks like this, that's the magnitude of A omega. We have not yet looked at the phase, but that's okay. We said the height of that will be whatever the area under the curve was, right, by definition, which if you leave the area under the curve equal to 1, it's just 1. And we said the first zero crossing happened at, help me out here, pi over A? I'm going to say yes. Right, because A omega had to equal pi. A omega equal pi, so omega was pi over A, yeah. In radians per second. Okay? So that's what we've discussed. And we discussed using the my FFT function in Matlab. And remember, what the my FFT function does is it basically calls the built-in FFT function, which is a not specific to Matlab. It's a well-known algorithm that exists, you know, it's been written in every computer language probably for the last 45 years maybe. I don't know. Matlab has a built-in implementation of it. But it's a pretty simple algorithm. You could write it in C, Fortran, like whatever you want. And the other thing my FFT does is it does this convenient thing of it creates a frequency vector. Okay, so that when you get the results back from my FFT, you can basically plot frequency versus the magnitude of A, and you can plot frequency versus the phase angle of A. Because remember, by definition, your Fourier transform A is a complex number, or a complex function rather, meaning that when you plot it, you've always got to do two plots to have the complete picture. You've got to have the magnitude plot and you've got to have the phase plot in order to get the whole picture. This is all summary, right? This is all stuff that we've talked about. I'm just kind of reminding you so there's a little overlap between the last lecture and that you remember all this stuff. Now, the last piece of the puzzle was that in order to run the myFFT command, we had to pass it 2 bits of information. Not only the signal that we wanted to take the Fourier transform of, but also the sampling frequency, right? And the sampling frequency happens to refer to how tightly spaced the points are on my original time function, okay? And it turns out it makes a big difference whether those points are really tightly packed together or whether they're a little bit more spread out, right? You imagine if they're more spread out, that's a whole lot different than if they're more packed in there. So I just wanted to bring to your attention, there's basically 2 ways to define a time vector in Matlab, and they do different things. So far we've been using the linspace command, right? So let's say our goal was to create a time vector from, let's say, -1 to 1, for example. Okay? So you could do one of 2 things. You could come and say t equals linspace -1, comma 1, comma number of points, right? So you'd say the number of points that would be between -1 and 1. So let's say for the sake of argument we said 5. I only want 5 points. Just because I'm trying to make an example here, not because that's actually like a good number of points to use. That's actually an awful number of points to use. Okay, so if I did this, what would be my first point in t? -1. And I've got a total of 5 points. So I've got -1, then I've got second point, third point, fourth point. What's my fifth point? 1. Okay, can somebody tell me how to calculate what the points are in the middle?
Negative 1 plus 2
Negative 1 plus 2
fifths.
fifths?
Oh, yeah, because you have to like take the whole length and divide by 5, and that's your, how do you call that again? Your dt.
Okay, so tell me what number to put here.
Negative 1 plus 1.
So what's my whole length here? 2. Right, I'm going from negative 1 to 1. That's 2 units.
Wait, wouldn't 0 be in the middle? Actually, yeah.
Would 0 be in the middle?
So then we'd have 0.5 and negative 0.5.
Point.
No.
Yeah, I mean, are they evenly spaced? The only rule that linspace puts forth is that they're evenly spaced, right? So that means that the difference between every set of adjacent points is the same. Now, is that what happened here? Yeah, right? Every time you add a half, right? Minus 1 plus a half, plus a half, plus a half, plus a half. Okay? So you specify the first point, you specify the last point, but what's the magic-y bit here is that Matlab calculates what like the spacing between the numbers has to be. Matlab calculates the dt. Okay, in order for you to have this first point, this last point, and a total of 5 points. It's not hard, it's not a tough calculation, but Matlab does the calculation for you. So what, sorry, let me get the mic back on. I can't do 2 things at once, apparently. Okay, so in this case, what's my dt? Right, so what does that mean? dt. That means the spacing between points is half a second. How many points per second do I have? 2. So if you take the reciprocal of dt, you get 2. So this is so dt is in the units of that is seconds per sample. Right? Each sample is worth half a second. If you take the reciprocal of that, you get 2 samples per second, and that's your sampling frequency. So look, for every second's worth of time, you've got 2 samples, right? You start at 0. If you wait 2 samples, you get to 1. Okay, so that's 2 samples per second. So now let's specify. So in this method, we were able to specify the number of points, and then Matlab calculates dt for you. Okay, there's another way. This bobby pin's not getting along with me today. All right, let's try that. That's a little bit more severe. All right, so there's another method. The second method works like this. Suppose you come along to Matlab and specify a sampling frequency. What should we specify our sampling frequency to be? Whatever you want. I'm just saying. Let's just pick a number that's reasonable because I'm going to write these out. Half a sample per second? It's a bit low. 10? Let's say 3. That's a nice non-round number that's going to make my life miserable, but that's okay. Okay, 3 samples per second. So you come along and you say fs equals 3, and then you say dt equals, yeah, or you just say 1 over fs, right? Don't type it in yourself. Let the computer do the work. And that way, if you change your value of fs, you don't have to change this line of code. Now watch what you do. You come along and you say t equals, I want a vector that starts at -1, colon, increment by dt, whatever that is, and I want to stop when I get to 1. Okay? So this says start at -1, end at 1, space according to dt. Beautiful. Okay, well let's try this. So what will my first point be? Negative 1 by definition. Okay, my next point will be negative 2/3, negative 1/3, 0, 1/3, 2/3, 1. Good. Now, here's the key difference between these two ways. And they're both fine, right? Both of them created a list of times, and that's totally cool. Now, here's the difference between the two. Up here, we specified the number of points, and Matlab calculated the dt. Down here, or instead of saying it calculated the dt, you could also say it basically calculated the fs. That's the same thing. Down here, it's like the opposite. Here, you specify the fs, and Matlab determines the number of points. You see the difference? Up here you say, I want 5 points. Matlab says, sit tight, I'll figure it out for you. Okay? Down here, you say, I want a sampling frequency of 3. Matlab says, sit tight, I'll figure out how many points that's going to require. You see the difference? So here you specify the number of points, here you specify the sampling frequency. So, neither one's right or wrong, they're both fine. Sometimes, in fact most of the time for signal processing, it's usually a little handier to be able to specify the sampling frequency yourself. Okay, because it turns out that the sampling frequency has some important properties in terms of defining your signals, and we're going to get into that as the semester progresses. So being able to specify the sampling frequency yourself is pretty important. But it's hard to beat the simplicity of lin space, right? If you're just looking for like a quick and dirty solution to something, just get a time vector going, it's pretty easy to deal with. All right? So, you know, again, the downside of using lin space is you might wind up with some sampling frequency that you're not real happy with. Like it's either too low or too high or something. So here you get control over your sampling frequency. But again, if you do it this way and you're not careful, you might wind up with like 10 million points, okay? Because you weren't really paying attention. And here you're not setting the number of points, you're setting the sampling frequency. Okay, up here you'll never have that problem because you would never be stupid enough to tell Matlab you want 10 million points. Okay, so there's no right or wrong, I'm just showing you two ways to do it. Now, is there any guarantee this last number will be 1? No. What if my dt, for the sake of argument, was, suppose my dt was 0.4. I think this will work out. Let's see what happens. If dt was 0.4, my first number would be negative 1. Okay, I'm guaranteeing that. Then I'd get negative 0.6, negative 0.2, 0.2. Oh crap, this is going to work, isn't it? Ah! How did that work?
4 goes into 20.
Boo! 4 goes into 20, thank you. Bad professor. Okay, let's say dt is 0.3. There you go. I'll get the last laugh. Okay, so negative 1, negative 0.7, negative 0.4, negative 0.1, 0.2, 0.5, 0.7. No? Did I do it again?
No, 0.8 instead.
Oh, thank you, thank you. 0.8, and then what happens?
Then
1.1?
will it stop before 1 or
Ah, it will stop before this number.
Okay.
It will say, this is basically saying, start at negative 1, don't exceed 1. So it'll basically stop here. So you're actually not even getting a guarantee. So when you use this notation, you're not even getting a guarantee of the last number will be equal to 1. Yes?
Can this accumulate floating point errors if you've got a really large amount of...
Yes! And there's like a whole theory about how to deal with this. Okay, so the question is about accumulating floating point errors. Yeah, there's, do I want to get into this aside? Yeah, I don't know if this method gives you floating point errors.
I think I used that in the computer assignment. I got an off by 1 because of all the round off errors.
Right.
So I had to go in and change the size of the thing to match the original thing.
Interesting. I think, I don't know whether this particular, I don't know quite how this particular method handles round-off errors, but I know in general that that is a problem that people need to be aware of. Yeah, I think it might actually. I don't.
I think what I was trying to do something with integers in it. I got really annoyed because it was using doubles, so it was giving me all these weird floating point numbers when normally you just use integers for it.
Oh, I see. Okay. Well, anyway, so, nuances notwithstanding. So using this knowledge, let's go back and look at, let's go play with Matlab for a little bit.
Thanks for asking.
Is it coming? Is it coming? So everybody says, hey, look at that. Slowly but surely. It's better than the other classroom I teach in. In 309, click the projector on, go get a cup of coffee, come back. All right. So let's go ahead and make that square pulse that we talked about, all right? So I need a time vector. That's the first thing I need. How shall I make my time vector? Should we use the FS method? Let's live dangerously. So FS equals, I don't know, let's have 1,000 points per second. Now I don't know if that's a good value or not, but if I leave it as a variable, then I can just go back and change that one number and it won't make any difference. So what's my dt going to be equal to? 1 over fs. You notice I didn't go type 1 over 1,000 or 0.001, right? Because that's sloppy coding. You want to make it so that if you change your sampling frequency that you don't have to go back through your code and change a million things, right? Just leave it as 1 over fs and that's it. You can change your sampling frequency after that. It will make a difference. Let's say t equals minus 1 to 1. Actually, let's do this. You saw how on the board I made it minus a to a? Okay, why don't I just make a variable as well? Let's say a equals 1. And I'm going to have my time vector go from minus 10 to dt to 10. So I'm going to make a time vector that goes from minus 10 to 10, and then I'll specify a. Okay, I'll make a variable that I can change. So x equals 0 times t, and then x of absolute value of t less than a equals 1 over 2a. All right, let me just make sure this plot's right, and then I'll tell you what I did. Ooh la la, very nice. Axis, minus 10 to 10, 0 to 5. Really? Oh, I suppose that would be a problem. Okay, so who can tell me what on earth I was thinking when I created the signal x? How did I do it? I did it in 2 lines.
You made it 1/2 of a whenever you have the absolute value being less than 1 of a.
Yeah. So first I made x equal to all zeros, right? How many zeros? I don't know, but it's the same number of zeros that t has. And that's kind of a crucial point. So over here, I said I want t to go from minus 10 to 10 with a spacing of dt. I don't know how many points that is, but I want you to figure it out for me. I mean, I'm smart. I can figure out how many points it is, but I didn't personally have to sit and worry about it. The computer worried about it for me. I mean, I'm going from minus 10 to 10. That's 20 seconds. Each second has 1,000 points. So roughly, I'm expecting 20,000 points, probably 20,001 to be exact. But the point is, I don't have to deal with that detail. So x should start out by being the same number of zeros as t, 20,000 points. And then what I'm saying is, I want you to go to x. I know I just defined x as all zeros, but I want you to find not all values of x, just some values of x. I want you to find for me those values of x for whom the absolute value of t is less than 1. Okay, so that would be points like 0, 0.5, 0.75, but also minus 0.5, minus 0.75. Those numbers have an absolute value that's less than 1. So that's going to find for me, in essence, all the numbers between minus a and a. And what do I want to do with those values of x? I want to set them equal to 1 over the quantity 2a. And that's how I got my rectangle. What's the deal with these parentheses? Do I need those parentheses, or am I just being, am I showing off?
You need those parentheses.
I need them? What happens if I don't put those parentheses?
Yeah, it's 1/2 times.
Right, if I don't do that, I get 1/2 times a, which is basically a over 2, which is not what I want. If I do it this way, I'm guaranteeing that it does 1 over the quantity 2a. All right, and there's my plot, and that looks good. Turns out I want to put my plot, I'm just going to adjust my axes a little bit. So subplot 3, 1, 1. All right, and what should I put on my x-axis here? What should I label my x-axis? Time in seconds. And all right, how's that? Nice and professional? Good. Now, let's create the Fourier transform and see if it is in fact what we expect. All right? So here we go. If we do that, we're going to say capital X. I can call this whatever I want. I just like to, my own personal method for keeping this straight is I use lowercase variables for time functions and uppercase variable names for frequency functions. So x comma f equals my FFT, and I'm going to pass my FFT two variables. The first is the array x that I want to take its transform of, and the second is the sampling frequency. Now, because I've already assigned the sampling frequency, I don't have to calculate it. You remember on Friday when we did this, we used the linspace method, which meant that before we could pass the sampling frequency to the FFT function, I actually had to stop and calculate what that was by calculating dt and then taking its reciprocal. Nice thing about this method is I don't have to do that. It's there for me. So subplot, and now I'm going to plot f comma absolute value of x. And what is that? No, seriously, what is that? Is that right?
Yes. The thing function, but
It's a mushed together sing function? Yeah. So notice something interesting. What was my sampling frequency? It was 1,000, right? Look at the frequencies on my x-axis. Minus 500 to 500. You think that's related somehow to Fs? Uh-huh. Uh-huh. What do you think would happen if I made my Fs equal to 2,000? What would be my frequency axis now? Yeah. Minus 1,000 to 1,000. What if I made my sampling frequency, I don't know, 250? Minus 125 to 125. So basically, whatever your sampling frequency is, it looks like your frequency axis goes from minus half the sampling frequency to plus half the sampling frequency. Now, if I set a equals to 1, what's going to be what value is the first frequency? What's the value of the first frequency, the zero crossing I'm expecting? Right, it's pi over, remember we said the zero crossings for the sinc functions should be at pi over a. In this case, a is 1, so that's pi radians per second, right? Pi, 2 pi, 3 pi radians per second. What's my x-axis in units of? Hertz, right? My FFT returns frequency in hertz. So if I'm expecting my first zero crossing at pi radians per second, how many hertz is that? Divide by 2 pi. So if I take pi and divide by 2 pi, 1 over 2. I'm expecting my first zero crossing at a half. So yeah, if you're expecting your zero crossings at a half, 1, 1.5, 2, of course I'm not going to be able to see that when my frequency axis is stretched out from minus 500 to 500. So clearly my problem is you just need to zoom in a little bit. Let's zoom in a little bit. Let's see, axis, I don't know, minus 10 to 10, minus 0.1 to, let's see, 1.1. Hey, look at that. Let's zoom in even a little bit further. What do you think? Is that what we anticipated? Is it a sinc function? Yes. Is the height the value that you expect? The height of that sinc function should be the area under the curve. And we've selected our area under the curve, under the square pulse, to be 1. Right? Because it's still got a width of 2a and a height of 1 over 2a. So that's width times height gives you 1. And we said we expected our zero crossings to be at pi over a. Remember we said zero crossings were at pi over a. It's behind the board now. We said zero crossings were going to be at pi over a radians per second. Okay, pi over a, 2 pi over a. That was in radians per second. But we're not looking at radians per second now. We're looking at hertz. So to get it in hertz, I'm going to take these values and divide by 2 pi. So that means my zero crossings are going to be at 1 over 2a, 1 over a, 3 over 2a. And if a is 1, that's going to be a half a hertz, 1 hertz, 3 half hertz, etc. And that is exactly what I'm seeing. First zero crossings at half a hertz. 1, 1.5, 2, 2.5, 3, so on and so forth. So am I getting what I expect? Absolutely. Not close. I'm getting exactly what I expect. Which is nice. Okay. How should I label my, I'm going to label my x-axis. What should I write on my x-axis? Frequency in hertz. Thank you. How we looking? It's nice, right? So all we're really doing, we're not learning anything new necessarily. We're just validating the technique that, for putting the signal in here. What do you think? You guys okay? Is your X signal the same as mine? Did you make sure you did the 1 over 2a part properly? Yes, sir.
I have an undefined function on my FFT.
Yeah, you have to download my FFT from Blackboard. It's not a built-in function. I wrote it. That's why it's my FFT. No. My FFT is a function that I wrote, which calls the built-in FFT function and adds a little bit of functionality to it. If you can't find it, I'll help you after class tweak the code. Okay. All right, what am I going to put in my third axis? Yeah, I'm going to put a third axis down here at the bottom now. What goes there? The phase angle plot. Because remember, it's not really complete until you do the magnitude and the phase. So let me cut and paste my code here. Copy, paste. So all I got to do is, instead of saying f comma absolute value of x, I'm going to say f comma angle of x. I'm going to hold off on messing with the... Oops, I left something out here. That should be the magnitude of f of x. And let's just hold off on that for a second, too. Wow! That's kind of cool. Should we zoom in a little bit? X lim minus 5 to 5. Let's zoom in at the same frequency. Holy moly. What have I done? That's not a rhetorical question. What have I done? Just kidding. I know what I've done. And I don't want to talk about it right now. Although this is going to be a cool little segue for later. But that is my frequency plot, believe it or not. And I don't want to talk about it. Not because I don't understand it or I'm scared of it. I just don't want to talk about it right now. I want to talk about other stuff first, and then we'll talk about why that plot looks crazy. All right, but believe it or not, there's lots of useful information packed in there that will provide a neat example for us. Okay, so we're just going to keep that down there for completeness and so that I have the code in there. And but right now I want to vary the value of a. So I'm going to make a bigger, little a. Okay, remember a is the width of my function. If I make a bigger, no, I'm going to make a smaller. I beg your pardon. If I make a smaller, so my first question is, if I make a smaller, what happens to my time function? It'll be higher and skinnier. If a gets smaller, it's going to get shorter and taller. Okay. As I do that, what is going to happen to my frequency function, the middle plot? Right. What will be the, okay, so we agree that the zero crossings are at going to be pi over a radians per second, and if I make a smaller, then pi over a should get bigger, meaning that those zero crossings should spread out. What about the height of the function? Yeah, the same. As long as I keep the area at 1, the height of that function should stay the same. Let's try it, see what happens. So this is a cool little button here. I don't know if I've shown you this before. But I'm going to put my cursor next to the 1, and then I'm going to click this divide button. And what that's going to do is, it's going to take my value of a, divide it by 1.1, and rerun my script, which is pretty cool, right? That's going to do like a whole bunch of stuff for me at once. And then we're going to look at how the plot changes. So here we go. What's happening? Is it doing what we expected? Sure is. Okay, so my time signal is getting taller and skinnier. And as advertised, my frequency signal is getting all stretchy. Now, I have 2 goals for you for today. One goal, and I think we can understand mathematically what's going on, right? It's pi over a is the zero crossings, and we can all understand that as a gets smaller, pi over a gets bigger. Okay, so I have two real goals for you. Screw the math for a minute. What I really want to know is why this makes sense intuitively is step 1. And step 2, what happens in the freaky deaky case where a gets so small that it basically goes to 0? So, okay, let's start with the a goes to 0 bit. So if a goes to 0, what's going to happen to my rectangular pulse?
It goes to an impulse function.
Impulse function? What's an impulse function? Yay! You folks sound like you've heard of an impulse function before. They still teach that in the math department? Diffie Q. Look at that. Like real engineers. Yeah. So this impulse function is going to own your life for a couple semesters, right? It turns out it's pretty vitally important to the engineers. So an impulse function is basically a function that has three qualities. It has zero width, it has infinite height, but here's the trippy part. What's its area? Finite. Thanks, calculus. Okay. Only in calculus can you have a rectangle with zero width, infinite length, and when you multiply 0 times infinity, you get a number, like a finite number. Okay, that's the joy of calculus. Okay, so that's what an impulse function is. So if we were to plot it versus time, the way we would draw it is like that. Okay, and notice I didn't say the area under that impulse was 1, because you can have impulses whose areas is 2 and 3.5, and believe it or not, you can even have impulses whose areas are negative. Let that sink in for a minute. Okay, but the point is that it's got some sort of finite area. It just happens to be infinitely skinny and infinitely tall. All right, and the way we write this is delta of t. Okay, delta of t is literally that's the impulse function. All right, and if your impulse has, so delta of t by itself refers to an impulse with area 1. If you have some other area, you just multiply it. So if I say like 3.5 delta t, that's an impulse whose area is 3.5. The other thing about delta t is that the impulse is always located at t equals 0. What if I want to put my impulse somewhere else? Time shift, right? So if I say delta of t minus 1, that's an impulse who's located at t equals 1. Am I obliged? Okay, so the other bit that's weird about this is that I can have impulse functions as functions of anything. So right now we're talking about impulse functions with respect to time, but quite frankly, I can also have an impulse function that's a function of frequency. Can I not? In fact, we've seen this before already. When I have a cosine, right? When I have cosine 3t, and I say take its Fourier transform, guess what you have? An impulse at omega equals 3, and an impulse at omega equals negative 3. So if I say take the Fourier transform of this, instead of drawing your two little sticks, what you could say is, well, I've got one impulse located at omega equals positive 3, and I've got another impulse at omega equals negative 3. It's pretty tight. And the area of each of those impulses is a half. Pretty cool. Okay, so long story short, if we let A go to 0, our little rectangle turns into an impulse. And as it turns into an impulse, that's really funny. You can't see that. It looks like it says lime, not time, which is kind of funny. Okay, so as I let my rectangle become an impulse, what happens to, does that help? Okay. As that becomes an impulse, what happens to my frequency content of that signal? Like right. If I keep making this skinnier and skinnier, this keeps getting wider and wider. And in the limit that A goes to 0, what do you think is going to happen to this one?
Energy at every frequency.
Right. What? I mean, we said our first 0 crossing is a pi over A.
What are those energy at every frequency?
But now there's literally energy at every frequency, not like.
And the magnitude's the same everywhere.
Yeah. So right. That's the difference. Right. So if we said, remember, we said our zero crossings are at pi over a. If a goes to 0, what is your first zero crossing? Never. It's at infinity. This is important. This is a fundamental property that we're talking about. If your signal x of t is the impulse function in time, so if you take a signal that looks like that and take its Fourier transform, you get a sinc function that never actually sinks. Right? If this kept getting broader and broader and broader, we kept stretching it and stretching it and stretching it, it would stretch so much that it would basically be a constant. And there you go. So, the Fourier transform of an impulse is, so this is an impulse. This is a constant. So, this is really cool. An impulse is this freaky function that has this amazing property that it has equal energy at all frequencies. And I mean all frequencies. You can't actually make one of these in real life, right? There's no button on your function generator that says impulses. So this is largely a mathematical tool, but it's a phenomenally valuable one, right? An impulse has this really amazing property that it has all frequencies in it at the same time. Why do you think that might be handy? Yeah? So go ahead.
If you want to like add an offset to your frequency response.
Not that.
If you want to figure out how a system would respond to any frequencies, if you were able to feed it an impulse, you could see what it would do to any frequency you feed in.
Kind of, yeah. So, for example, suppose you had some unknown system. All right? And I said, the properties of this function vary as a function of frequency. So it's a filter. Some frequencies are passed, some frequencies are rejected. Please help me figure out what's going on in this box. Okay? As of this morning, you would have said, oh, okay, I know what to do. I'm going to create a 1 hertz cosine, and I'm going to see what comes out the other end. I'll measure it. Oh, look, it looks like that came out exactly as it went in. Then I'm going to make a 2 hertz sine. Then a 4 hertz, then a whatever, all the way down to a megahertz, right? I'm going to try all these different frequencies and see which ones are passed and which ones are rejected, okay? And you'll get the right answer. However, it turns out that there is a cool method where you can try all those frequencies at the same time. All you got to do is put in an impulse. Why? Because an impulse is simultaneously a cosine at 1 hertz, 2 hertz, 3 hertz, 4 hertz, all the way up to a gazillion hertz. It contains all frequencies at equal energy. So you take your impulse, you stick it in, you measure what comes out, and that's it. You know the system's response to every frequency. That's powerful. Very powerful. And we're actually going to talk about how to do that, like actually with numbers. Yes?
So what if you want what if you don't want every frequency? What if you want a specific bandwidth to go into that block?
Well, right now I'm just trying to do a technique where I figure out how it responds to all frequencies. So, I mean, you could always go back and do, other methods of testing it and so on and so forth. But mathematically, at least, this method will give you that tool to understand the system's responses to all frequencies, okay, without any loss of generality, without any loss of anything. So that's pretty awesome. Let's go back the other way real quick. So that was the first thing I wanted to make sure that I cover today, right, is that what happens when a goes to 0. So the other thing I want to talk about is intuitively, does it make any sense intuitively, not mathematically? I know mathematically it's just an equation and we got our heads wrapped around that equation. But intuitively, Can somebody tell me why it should be that making a pulse skinnier means that the frequency gets stretched? Why is that a reasonable thing to expect?
Infinitely high, because we always said like high frequencies, like for the square wave, were at where it changes, you know, at the edge there. So if it's infinitely high, you're going to use infinitely high frequencies.
But don't let it go to infinity. I mean, you're right, but I'm saying let's just back off from infinity for a second. Like, let's just walk back from that conversation. Let's just have the general conversation that as the pulse gets skinnier, why does the frequency get stretchier? Not because it converges to the impulse. I mean, I think you're on the right lines.
That's where I was going with that.
Okay.
You can derive any frequency by a finite point.
Okay.
Because the square is getting, the width of the square is getting so small that the corners are pretty much, you don't need any corners, so you could take every frequencies to make those corners.
You're kind of all dancing around the right
If
answer.
you were to rebuild it out of cosines, an infinite number of them, then you'd have to get higher frequency cosines, so therefore you have to have more energy and more frequency.
Yeah.
It's 1 over t, period.
Yeah.
So literally that relationship. So as the denominator gets bigger.
Yeah.
I figured that was the mathematical method.
Right. Okay. So here's a rectangle. Let's say I want to make this rectangle out of cosines, right? So if I want to rebuild this out of cosines, probably like one of the cosines that I'm going to want to use might look like this. Okay. Now that cosine obviously does a pretty bad job of. I mean, it gives me sort of like this peak and this point down here, but then I'm going to need some higher frequency cosines to deal with all the other bits. So you keep adding cosines. But let's just think about this cosine first, okay? Now, if instead I make my pulse skinnier, and I try to fit it with a cosine, so this is case A, this is case B. Which one has the higher frequency cosine? B, right? Here I had a wide, it was broad in time, but it had a low frequency cosine, right? This is my cosine, and it's see how that's a much lower frequency cosine than this one? This is a high frequency cosine. And that's the general pattern. As you make your signal skinnier, you're obliged to fit it with higher frequency cosines. And isn't that what's happening when you make this pulse, when you make this sinc function wider? What that's telling you is that you have more energy. You're pulling your energy out to higher frequencies, right? Before, when this thing was all mushed together, all the energy was packed in the middle at low frequencies, and there was basically no energy at high frequencies. Now I'm saying, well, I've stretched it. That means that I'm stretching my energy out to high frequencies, which is exactly what would need to happen if your pulse gets skinnier, okay? So this is one of these vital kind of core properties of signal processing that is sort of like easy to explain, but it takes a while to internalize it and realize why it's valuable, is that the skinnier pulses become in time, the more frequency content they contain, the broader they become in the frequency domain. That's going to wind up having some really important implications for a variety of things. In fact, maybe we'll actually do an example of that on Wednesday, although I do want to make sure I spend some time figuring out what went on with this angle function. So we will start with this, though, on Wednesday. So today we took our rectangular pulse and we made it skinny. So on Wednesday we'll start by taking our rectangular pulse and making it wide. Okay? And you should be able to guess what's going to happen because we've already done it. We already know the answer. Okay? But it's just nice that it happens to be consistent with something that we already know. All right, I'll see you on Wednesday.
After
Yes, sir.